Duality property of Fourier transform. The Fourier transform of small x of t is denoted by capital X of omega, where omega is frequency in radian per second. Now, according to the duality property of Fourier transform of capital X of t is 2 pi small x of minus omega. Now, let us see the proof of this duality property of Fourier transform. We know that the Fourier transform of small x of t is integration of xt into e raised to the power minus j omega t with respect to t, where t is changing from minus infinity to t. Similarly, the Fourier transform of capital X of t is integration of capital X of t into e raised to the power minus j omega t with respect to t, where t is changing from minus infinity to t, minus infinity to plus infinity. Now, the inverse Fourier transform of capital X of omega is small x of t, and it is given by 1 over 2 pi integration of capital X of omega into e raised to the power j omega t with respect to omega, where omega is changing from minus infinity to plus infinity. Now, in this expression of xt, we will simply replace t by minus k. Now, the new expression will be x of minus k, which is equal to 1 over 2 pi integration of capital X of omega into e raised to the power j omega minus k with respect to omega, where omega is changing from minus infinity to plus infinity. Now, this minus sign, we will bring this minus sign in front of j. So, this will be the new expression. Now, here we will replace omega. In fact, we will bring this 2 pi on the left hand side. So, this will be the modified expression. Now, in this expression, we will replace omega by t. These three omegas are replaced by t. So, the modified expression, this will be the modified expression where omega, 3 omegas are replaced by t. Now, if we compare expression 4 with expression 2, we can see that this k is acting as omega. So, we will simply replace k by omega in the expression 4. Now, we have 2 pi small x of minus omega equal to integration of capital X of t into e raised to the power minus j omega t with respect to t, where t is changing from minus infinity to plus infinity, which is nothing but the Fourier transform of capital X of t. So, if Fourier transform of small x of t is capital X of omega, then by duality property of Fourier transform, the Fourier transform of capital X of t is simply 2 pi small x of minus omega. Now, we can see same property in terms of f, where f is in hertz. So, Fourier transform of small x of t is denoted by capital X of f. So, according to duality property of Fourier transform of capital X of t will be small x of minus f. We can see the proof of this duality property. Fourier transform of xt is integration of xt e raised to the power minus j 2 pi f t with respect to t, where t is changing from minus infinity to plus infinity. So, Fourier transform of capital X of t will be integration of capital X of t e raised to the power minus j 2 pi f t with respect to t, where t is changing from minus infinity to plus infinity. And the inverse Fourier transform of small x of t is inverse Fourier transform of capital X of f is small x of t, and the expression for this xt is integration of capital X of f into e raised to the power plus j 2 pi f t with respect to f, where f is changing from minus infinity to plus infinity. Now, in the expression of xt, we will replace the t by minus k. These two t's are replaced by minus k. So the new expression, this will be the new expression, x of minus k equal to integration of x of f into e raised to the power j 2 pi f minus k with respect to f, where f is changing from minus infinity to plus infinity. Now we will bring this negative sign in front of j. So this will be the new expression. Now we will replace f by t in this expression. So these three f's are replaced by t. So the modified expression, this will be the modified expression. Now we will compare the expression 4 with expression 2. We can see that this k is acting as f here. So we will replace k by f. So this expression, the new expression will be x of minus f equal to integration of x of t into e raised to the power minus j 2 pi f t with respect to t, where t is changing from minus infinity to plus infinity, which is nothing but the Fourier transform of capital X of t. So if Fourier transform of xt is xf, capital X of f, then Fourier transform of capital X of t is small x of minus f. Now let's see the example where we will find out the Fourier transform using the duality property. First is Fourier transform of 1. We know that the Fourier transform of del t is 1. Then by duality property, the Fourier transform of 1 will be 2 pi del of minus omega. Here del of minus omega, in fact del of omega is even function. So del of minus omega will be replaced by del omega. So Fourier transform of 1 will be 2 pi del omega. Now we can see the graph of this. This is del t impulse. Its Fourier transform is 1 for all frequencies. Now we will apply the duality property, and through duality property we will find out the Fourier transform of 1. So the Fourier transform of 1 is 2 pi del omega, where 2 pi del omega is impulse. Its value is non-zero at omega equal to 0, and it is 0 otherwise. Similarly, we can see the Fourier transform of 1 in terms of f. The Fourier transform of del t is 1. Now we will apply the duality property to find the Fourier transform of 1. So by duality property, Fourier transform of 1 is del of minus f, and del f is even function, so we can write the Fourier transform of 1 as del f. This is the plot for impulse. Its Fourier transform is 1 for all frequency. Now we will apply duality property to find out the Fourier transform of 1. So in time domain, signal is 1 for all time, and its Fourier transform is del f, which is impulse, which is non-zero at f equal to 0, and it is 0 otherwise. Now let's see another example. Fourier transform of sinc function. We know that the Fourier transform of a rectangular pulse is sinc of omega upon 2 pi. Now we will apply the duality property, where omega is replaced by t. So Fourier transform of sinc t upon 2 pi will be 2 pi rect of minus omega. Here rectangular pulse is also even function, so we can replace rect of minus omega by rect of omega. So Fourier transform of sinc t upon 2 pi is 2 pi rect of omega. Now let's see the plot. This is the rectangular pulse, which is 1 from minus 1 by 2 to plus 1 by 2 and 0 otherwise. And its Fourier transform is sinc function, sinc omega upon 2 pi. Now we will apply the duality property to find the Fourier transform of this sinc function, where omega is replaced by t. So the Fourier transform of sinc function is a rect pulse. Now we can see the Fourier transform of sinc function in terms of f also. Fourier transform of rect t is sinc f. By duality property, Fourier transform of sinc t is rect f. Rect f is even function. Now let's see the plot. This is the rectangular pulse. Its Fourier transform is sinc function. And by duality property, Fourier transform of this sinc function is rectangular pulse. Now let's come to the another example. Fourier transform of sinc squared function. We know that the Fourier transform of triangular pulse is sinc squared function, which is sinc square omega upon 2 pi. By duality property, the Fourier omega is replaced by t. Fourier transform of this sinc squared t upon 2 pi has to be 2 pi tri of minus omega, and triangular pulse is even function. So we can write the Fourier transform of sinc squared function as 2 pi tri omega. This is the plot for triangular pulse, and its Fourier transform is sinc squared function. Sinc squared function is square function, so it's all the values are positive. And to find the Fourier transform of this sinc squared function, omega is replaced by t, and its Fourier transform is triangular pulse. Now we can see the Fourier transform of sinc squared function in terms of f also. Fourier transform of triangular pulse is sinc squared f. By duality property, f is replaced by t. So Fourier transform of sinc squared t is tri of minus f, and this triangular pulse is even function. So Fourier transform of sinc squared t is tri f. This is the plot for triangular pulse. Its Fourier transform is sinc squared function. By duality property, we will replace f by t. So the Fourier transform of sinc squared t is triangular pulse. So in this way, by applying the duality property, we can find out the Fourier transform of different functions. Thank you.